Welcome to Adventures in Math. In this episode, we explore a basic question that most of us take for granted. What's a number? The answer seems like it should be obvious, but descriptions of numbers as quantities or sequences of digits fall short. To put it simply, numbers are objects that exist in the abstract universe of mathematics, just like any ordinary everyday object, like an apple sitting on your kitchen counter. However, unlike the apple in your kitchen, we cannot see or interact with these abstract objects directly. We need a bridge from our world to the abstract world of numbers, a concrete representation that we can interact with. Let's start with the number one. First, we've already stated that numbers are objects. Through this view, the number one is a unique mathematical object, and we are simply giving it multiple names. For example, the English word one or the digit one. Even though there is only one object corresponding to the number one, it has many representations or names. There are an infinite number of ways to express the number one. We list a few different ways here. Numbers are often conflated with their decimal representations, since we frequently encounter them in that form in everyday life. However, the decimal representation is just another name for the same number. Curiously, this has led to a topic of immense debate online. Does 1 equal zero point 0.9 repeating? The main point of contention here is that the two forms appear different, and there is a subtle involvement of an infinite process. There are many excellent videos that go into detail proving this fact. For completeness, here is a simple argument. First, we'll start by defining x to be 0.9 repeating. Then we'll multiply both sides of this equation by 10 to get 10x is equal to 9.99 repeating. Now subtract the first equation from the second. Well, we get 10x minus x, and we get 9.9 repeating minus 0.9 repeating. This gives us 9 times x is equal to 9, which simplifies to x equals 1, which then gives us 1 equals 0.9 repeating. If you still aren't convinced, take a look at the many videos online that present a variety of proofs. For our purposes, this is simply an illustration of the number 1 having multiple names, even though it is a unique mathematical object. We know that there are special numbers, like pi and e, that have no apparent pattern in their decimal expansions, and we'll explore them in more detail throughout our adventures. One special number, phi, the golden ratio, has a simple, predictable pattern even though it is irrational. The simplicity of the pattern only becomes apparent when we write phi in certain ways. In particular, we'll look at what is called the continued fraction representation of a number, which will clearly reveal the pattern. First, let's define the golden ratio, a number that connects to the spirals of galaxies in the Fibonacci sequence. Imagine a rectangle where the shorter side is length a, and the longer side is length a plus b. When the ratio of the longer side to a is the same as the ratio of a to b, we call this value the golden ratio, or phi. That is, phi is equal to a plus b over a, which is equal to a over b. Now let's solve for phi. We'll start with a plus b over a is equal to a over b. Then we'll multiply both sides by a over b to simplify things. And you can see the a's cancel, and b will become 1, and on the right-hand side, we'll get a over b squared. So we end up with a over b plus 1 equals a over b squared. Now from the definition of phi, we can substitute it in because it is a over b. So we have phi plus 1 is equal to phi squared. Finally, let's rearrange all of this, and we end up with a quadratic equation, phi squared minus phi minus 1 is equal to 0. Now let's quickly recall the quadratic formula. To solve a quadratic equation like the one we have here, we can use the formula x equals minus b plus or minus the square root of b squared minus 4ac, all divided by 2a. In our case, the coefficient for phi squared is just 1, so that means that a is equal to 1. The coefficient for phi is minus 1, so then b is equal to minus 1. And finally, the constant term is just minus 1, so c is equal to minus 1. We can plug all of this in to our formula, and what we'll end up with is 1 plus or minus the square root of 5 divided by 2. Since phi is positive, we have phi equal to 1 plus square root of 5 over 2. And this is approximately 1.618, and it keeps going with no immediately recognizable pattern. The other root that we can find here is 1 minus square root of 5 divided by 2. And it has a beautiful property that it is equal to 1 minus phi, which is actually equal to minus 1 over phi. Now we have defined phi and found its decimal expansion. There's no immediately obvious pattern in the digits. Let's define the concept of a continued fraction and see what it reveals about the golden ratio. We can write a continued fraction as a0 plus 1 over a1 plus 1 over a2 plus 1 over and so on. Or with a convenient shorthand, we can write a0 semicolon, a1 comma, a2 comma, and so on. Now let's make this concrete using a simple fraction. Let's choose 1/3. Now 1/3 is going to be equal to 0 semicolon 3. We can see that the continued fraction terminates. This will be true for any rational number. For irrational numbers like phi, we will get an infinite sequence. When we compute the continued fraction for phi, we find a surprisingly simple pattern. Phi is equal to 1, 1, 1, and 1s all the way on. Despite being irrational, it's simply an infinite sequence of 1s. Another similar way to define the golden ratio is as nested radicals involving only 1. Phi is equal to the square root of 1 plus the square root of 1 plus the square root of 1 plus, and so on. In this episode, we started with a simple question. What is a number? We explored the concepts of mathematical objects and their concrete representations. The key takeaway is that numbers exist on their own, and we are simply naming or describing them in different equivalent ways. In our next adventure, we'll examine different kinds of numbers, a naturally emergent hierarchy, and how it all connects to the concept of infinity. If you enjoyed the video, don't forget to like and subscribe.